Here in this example, we have two spheres, A and B is moving to the left with an initial speed of VB1. Sphere A is initially moving to the right with some speed of VA1. And one thing that we know is the line of action, the motion for B, just moves along this line, which is at the very bottom of A. We'll use that in just a bit when we do some trig. But what we want to know is that in addition to that information and the coefficient of restitution being 0.6, we want to find the velocity of each of the spheres after impact occurs. So as we've seen on looking at problems in impact, the free body diagrams that we need generally are the free body diagrams of each particle individually, as well as a free body diagram of both of them together. And we'll see the roles that's played by each one of those as we work through this. So the first thing I'm going to do is look at the FBD of A and B together. Well, there are no forces acting on it from the outside. So that's going to play a big role in what conservation of momentum equation that we can use. However, if we look at A by itself, then we have this impact force, FAB. Since there's no friction acting between A and B, the impact force lies along the line of impact. In other words, it's perpendicular to the plane of contact. Then by Newton's third law, then the equal and opposite force on B is like that. What we're going to do is talk about the resolution of forces and velocities in terms of vectors components which are tangent to the plane of contact, that's T, and N, which is the line of impact. So I'm going to label all these axes as this. Okay, so based on our FBDs that we have, we're going to use linear impulse momentum equation as well as the coefficient of restitution equation. So if we look at, let's say, A by itself, the thing that we see is that when we sum forces in the direction T, there are no forces. So what this says is that momentum for A in the tangential direction is conserved during impact. So MAVA1T is equal to MAVA2T. Masses cancel out, of course. So it says then that VA2T is what it was beforehand. Okay. And what did we have before? Well, what we had before impact was VA1 is like this. So we need to be able to resolve that in terms of normal and tangential components. And this is where the trig comes in. If I construct a triangle, again noting that the path of B is passing through the bottom part, the bottom surface there of A, I can find this angle here of theta, because knowing the radius of A, that's given information, then this hypotenuse of the right triangle is RA plus RB. So from trig we can see here that sine of theta is equal to RA over RA plus RB. So from that trig we can find the angle. Okay, so that's the same angle here for the velocity of A relative to the normal direction. So what this says is that VA1T is equal to the initial speed itself projected along the T direction, which is going to be sine of theta. We do the same thing for B. the observation we make here is that we have this impact force, FAB, which we don't know. We don't want to deal with that. But it's only in N. That leaves no force acting on B by itself in the tangential direction. So MBVB1T is equal to MBVB2T. So just like it was for A, the tangential component of velocity after impact is the same as it was before. And what it was before was the initial speed VB and projected. That's this way here. So its tangential component is going to be a sign, S-I-N-E sign here, with a negative S-I-G-N sign there in front, because that's pointing in the negative T. So right away, of the four components we want to know, two components for A and two for B, we have two out of those four from using conservation of momentum on A and B together, or I'm sorry, individually. When we look at them together, then that normal force, FAB, is an internal force. It didn't appear on free body AB. So we can now say that the summation of forces on A and B together in the in direction is a zero. So that says that MA VA1N plus MB VB1N, that's the normal component of the momentum before, is equal to the normal component of the momentum after impact. So the right-hand side is like the left-hand side, except it's for after impact. And in addition to that, we have the coefficient of restitution equation, keeping in mind that that is only valid for the normal components. So VB2N minus VA2N divided by, with a normal component difference before, with the signs reversed. So this equation says, when I multiply it through, it's going to be an EVA1N minus EVB1N is equal to V minus VA2N plus VB2N. So from this we see we have two equations and we have two unknowns. So what I might recommend that we do is, let's say, multiply this whole equation here by MA. Okay, and when we get through, add that to the equation above. So what we have here is MA 1 plus EVA1N. The second term is going to be an MB 1 minus EVB1N. Again, all I'm doing is adding together the first equation with the second equation multiplied by MA. And the reason for doing that is that we see that when we add them, these will cancel out. On the right hand side, we simply have MB plus MA VB2N. So from this we get VB2N is equal to MA1 plus E VA1N plus MB times 1 minus E VB1N divided by the total mass here of MA plus MB. So this is just a process that we go through in order to solve those two equations. And then we can, let's say, take the second equation right here, and we can solve for VA2N, which is equal to VB2N minus E times VA1N minus VB1N. So now that we've solved for VB2N, we've got numbers we can use here, and keeping in mind that the normal component, the n component of the velocities beforehand, let's scroll back up here and see what those are. The normal component of VA1 is going to be VA1 cosine, and the normal component of velocity of B before impact is going to be minus VB1 cosine. So again, these are known pieces of information, and those go here and there to allow us to solve for VB2N and VA2N. So what did we do here? Well, the basic idea here, which is true for most problems we're going to deal with here in impact, is to first look at an FBD of A and B together, look at A by itself, look at B by itself. And what we get from our individual FBDs is the observation that the tangential component of velocity is unchanged by the impact. There's no forces acting there. So that's how we got this and this. By looking at A and B together, we now have conservation of momentum in N because there's no forces acting in N. They gave us this equation. And then fourth equation is the coefficient of restitution equation. The differences in the normal components of velocities divided after impact divided by the difference with a negative sign in front of the normal components of velocity before impact. That gives us our two equations. We solve for the normal components of VB2 and VA2. Again, using this trig that we went through to find the angle of impact, which gave us the normal components of VA1 and VB1.